Y Takamitsu pues dará la introducción.
Hola, sí, bienvenido, Yohana. Y el ponente es un estudiante de doctorado en la Leibniz-Institut für Astrophysik en Potsdam, Alemania. Es como mismo instituto que la Mirko Krumpe que dio seminario hace unas semanas. Y está nos visitando desde como hace 3 semanas, 2 semanas, 3 semanas. Y por un poquito más que un mes. Entonces, él estará aquí en la oficina de doctorado 404 hasta la fin de próxima semana. Entonces, allá. Entonces, su maestría fue 2019 y desde el proyecto de maestría estamos trabajando particularmente en la función de correlación o modelo de la Halo Occupation Distribution de la una muestra enorme de, ¿cómo se llama? Emisoras de Lyman-alpha observado con MUSE. Y es el tema de su tesis doctorado. Momentito, ella tendrá probablemente examen este verano. Okay. Okay, muy bien. Entonces, ahorita día, sí, ella presenta su proyecto de tesis. Okay.
Okay, so thank you, Takamitsu, for the nice introduction. And most importantly, also thank you for hosting me here during these couple of months. So as Takamitsu said, I'm going to tell you a bit about the work I've been doing during my PhD. So the general title I've given to the presentation is the clustering of MUSE Lyman-alpha meters at redshift from 3 to 6. And I've done this work together with Takamitsu, with Mirko, that was here a couple of weeks ago as well, with my supervisor, and also together with the MUSE collaboration. So this is the outline. Oh, it's not passing. Okay, it's going to go very slow. So this is the outline I'm going to follow in this presentation. I will first give you an introduction to clustering measurements. I will then move to the galaxies that I have focused during my whole PhD, the Lyman-alpha meters. And I will tell you a bit also on how to detect these galaxies. So mostly I will focus on the MUSE spectrograph, which is a spectrograph that detects these Lyman-alpha meters I'm using. I will also show you some of the most important Lyman-alpha meter clustering results that we found. I will also as well show how we have modeled the clustering of these Lyman-alpha meters, and I will finally give you some of the implications. And finally, I will just conclude the talk. So let me first just go to the introduction to clustering measurement. So what is clustering? So it was already in the 70s when people started to look at the sky with photometric plates in the first place. And they already saw from those first observations that galaxies do not seem to be randomly distributed. In fact, there are some regions of the sky where you see many galaxies, while in some other regions of the sky, you don't see barely any galaxy. So already in the 70s, people started to wonder whether galaxies are tracing some kind of structure of the universe. This became more clear with the first redshift surveys. I'm showing you here the CFA survey, where you see how galaxies are tracing these that we would call today a filament.
O sea, pierdo 20,000 pesos. O sea,
No? Okay. Then with the years, these instruments became better. The regions of the sky that were sampled became much larger as well. And for example, the 2DF spectrograph here already shows the clear large-scale structure of the universe that is being traced by the galaxies. So this is also what we would call today the cosmic web. And already in these days, you have surveys like the SDSS that mainly cover most of the sky, where you can clearly see this large-scale structure of this cosmic web of the universe. So this is the kind of information that clustering is going to give us. Clustering is going to tell us about this large-scale structure of the universe and also about the matter distribution of the universe. So when I say matter, I do not only mean baryonic matter, so the matter from the galaxies, but I also mean the dark matter distribution of the universe. So today, the generally accepted picture is that you have this structure of dark matter, and within those dark matter halos, you have galaxies. So in some way, galaxies are tracing the dark matter distribution of the universe. So by studying the clustering of these galaxies, I will not only trace the baryonic matter, but I will also trace the dark matter distribution of the universe. Now, we can measure the galaxy clustering at different scales, and that will provide different kind of information. So if we measure the galaxy clustering at larger scales, so scales larger than 1 comoving megaparsec or so, what we are going to obtain is the dark matter halo properties. And by properties, I mean things like the mass of the dark matter halos. So by studying the clustering at different redshift, as you can see here, I will be able to trace the dark matter evolution. So how the masses of the dark matter halos are evolving with time. And this is, of course, very relevant for cosmology. On the other hand, we can measure the galaxy clustering at the small scale. So scales smaller than 1 comoving megaparsec or so. And that will give me something called the halo occupation distribution. So that is that when we have a dark matter halo, galaxy clustering is going to be able to tell me how many galaxies you can populate this dark matter halo with. And that will become really important for galaxy formation and evolution theories. Not only galaxy clustering is relevant for these two areas, but we will see very briefly that this galaxy clustering affects things like luminosity function measurements, like the circumgalactic medium of galaxies and many other things that I will not have time to talk about. So, okay, we know why galaxy clustering is important. We also know what kind of information galaxy clustering provides. Now, how do we measure this clustering? So the way that people have commonly used this, have commonly measured the clustering of galaxies is by using 2-point correlation statistics. So this means that people measure the 2-point correlation function. And this function is just giving you an excess probability of finding a galaxy pair, so two distances, at that distance r in a given volume for a given number density. So let me just give you an example. If you have two galaxy samples, this one on the left and this one on the right, if you measure the 2-point correlation in these samples, this is what you are going to obtain. On the left one, you will obtain a 2-point correlation function that is larger than 0. And this will tell you that your objects are clustered. Your galaxies have some clustering, and therefore they are tracing some kind of structure in your sample. On the other hand, if you measure the 2-point correlation here, what you are going to obtain is a correlation function that equals 0. And this tells you that your galaxies are randomly distributed. They do not trace any kind of structure in the universe. However, this seems a bit theoretical, right? Like this excess probability, how do you really measure this in reality? So the way that people do this is by using some estimators. And the idea is the following. If this is your sample of galaxies, what you're going to do is you're going to count pairs of galaxies within your catalog. So we will sit in the first galaxy of your sample, and then you will count all possible pairs of galaxies that that galaxy in red here may belong to. So that will be our first galaxy pair, our second galaxy pair, our third galaxy pair, and so on. So you will do this for all the galaxies in your sample, and in the end, you will obtain something that we call DD, data pairs. Then you're going to create a random sample that somehow follows the redshift distribution of your original sample. And you will do the same. You will count all possible pairs of galaxies within your random sample. And once you're done with that, you obtain something called RR, so your random pairs. So now the 2-point correlation function is estimated in such a way that we compare the number of galaxy-galaxy pairs with the number of random-random pairs, and you estimate the two-point correlation function as a function of distance between your galaxy pairs. Now, the only issue here is that we cannot directly measure the distance between galaxy pairs in a direct way. So what we have to do is we take the redshifts of the galaxies, we assume some cosmological model, and from that we infer the distances from those redshifts of the galaxy. So if this is our galaxy pair, I'm going to compute two different kinds of distances, cosmological distances between the galaxy pair. I will calculate this one in red that I call R, so this is a transverse distance between galaxy pairs. And then I will calculate this other one that I call Z, and this is a line of sight distance between galaxy pairs. So in fact, in reality, we will be doing this counting of pairs in a 2D grid, in a grid for transverse and for line of sight distance as well. So this is all for the introduction. This is what clustering is telling us. This is how we measure clustering. Now, what is what we want to know? So some of the goals of my thesis were whether to investigate whether there is a structure in the high redshift universe, or in other words, are high redshift galaxies clustered? Then we also wanted to know which are the properties of the dark matter halos that host these high redshift galaxies. And we wanted to explore how galaxies are distributed within those dark matter halos. Then we also wanted to check whether this spatial distribution of the galaxies is independent on galaxy properties, or whether there is some dependence, and depending on the galaxy properties, results may change. And finally, we want to investigate whether this spatial distribution of the galaxies affects other fields of astronomy, like the circumgalactic medium of galaxies, that this is the only one I will mention in this talk. So let me just first move to the high redshift universe, and let's start where everything started. Let's start in the Big Bang. In the Big Bang, when the first protons and electrons were firstly created and were floating around this very hot plasma here. Once those electrons and protons recombined during their recombination phase, the universe became neutral, and this gave place to the dark ages. Then the first stars and galaxies started to form, and the photons coming from those stars and galaxies started to ionize the universe. So this is what is known as the reionization epoch. And this epoch is believed to have finished about a redshift of 6, or about 1 billion years after the Big Bang. And after that, the universe is fully ionized, and it continues evolving until today. So the galaxies I'm going to focus on are the Lyman-alpha meteors, and they are detected at a redshift between 3 to 6. So this means that we start detecting Lyman-alpha meteors when the reionization epoch finished, and we will go all the way down to a redshift of 3. But what are these Lyman-alpha meteors? So Lyman-alpha meteors are just galaxies that are detected through the Lyman-alpha emission. And to understand this Lyman-alpha emission, we need to think about the energy levels of a hydrogen atom. So if you have an excited hydrogen atom, when an electron comes down from the second excited state to the first state, it will emit a photon. And this photon is the Lyman-alpha photon. And in fact, this is the most common emission from the hydrogen atom. And actually 2/3 of all these recombinations will end up giving you a Lyman-alpha photon. So this Lyman-alpha emission has a wavelength of around 1,200 angstroms, which falls in the UV part of the spectrum. But we are pretty lucky because this emission is shifted into the optical when we go to very high redshifts. So when we go to a redshift of 3, this line that was belonging to the UV now is located in the optical. And this is why the Lyman-alpha emission is the most common line to detect high redshift galaxies from the Earth with ground-based telescopes. Now you have two ways of detecting these Lyman-alpha meteors. You can either use narrowband filters, or you can use spectroscopy. So if you have narrowband filters, I show you two examples of narrowband filters in here for a given wavelength width and also a given redshift width. So you put these filters in your instrument, you look at the sky, and you will obtain Lyman-alpha meteors that fall within this wavelength range, or that fall within this redshift range. So in that way, you obtain Just as an example here, these Lyman-alpha emitters that are all detected at a redshift of 6.5, a bit more. This is in all the spectra that you see here on the right, that is the Lyman-alpha emission. So the good thing about narrowband surveys for Lyman-alpha emitters is that they can cover or they can sample very large areas of the sky. The only problem, or the not so good thing, is that they only detect one redshift. So the redshift that comes determined by the filter width that you're using. So when they study the clustering of these Lyman-alpha emitters, they will study only a 2D universe. They only have the 2 spatial coordinates and one single redshift. On the other hand, you can use spectroscopy. You can use, for example, MUSE. MUSE is its meaning multi-unit spectroscopic explorer, and this spectrograph is located on the VLT in Chile. So this is an integral field spectrograph, and this means that when you look at the sky with the MUSE instrument, you are going to obtain a data cube that has 2 spatial coordinates, as you can see here, but they also come with a whole wavelength information. So for each single pixel of MUSE, you obtain a data cube with 3 coordinates. This is, of course, very expensive, this kind of spectroscopy. So the field of view has to be quite small. In the case of MUSE, you have 1 arc-minute square field of view. But the wavelength range, you can see it here, it's really large. And this wavelength range is ideal to detect Lyman-alpha emitters in a redshift from 3 to 6. So the great thing of MUSE is that now we can study a 3D universe with the 3 coordinates. But the spatial coverage that MUSE will cover is not that large. It's actually quite small, and it comes determined by the field of view of the instrument. So let me show you which kind of samples of Lyman-alpha emitters MUSE is detecting. So right now there are 3 MUSE surveys for Lyman-alpha emitters, and they are built following what is called a pencil beam survey design, or also what is called as a wedding cake approach. So if we think as a wedding cake, you have the base of your cake, which is the widest of all the surveys, but also the shallowest of all the surveys. So that is the case for MUSE Wide that you see here in red. It's the largest of all of them, 100 fields, meaning 100 square arc minutes coverage, but it has 1 hour exposure time. So on top of the base of your cake, you have a deeper survey, which is much smaller. And that is what we call MUSE Deep. And this is the green survey that you have here. Now we have 10 hours exposure, but we have a much smaller coverage. We only have 9 square arc minutes. And then you have the top of the cake, which is this in blue that you see here. And this is the MUSE Extremely Deep Field, or MXDF. And this is up to now the deepest ever performed spectroscopic survey for Lyman-alpha emitters. It has 140 hours, but is of course the smallest of all of them. It only has 1 field of coverage. Now, because of these different exposures of the 3 different surveys, the Lyman-alpha emitters that you are going to detect in each of these surveys have slightly different properties. So what I'm plotting on the y-axis is the Lyman-alpha luminosity, Scott, as a function of redshift of the surveys. And these dashed lines corresponds to the median luminosity of each of the samples. You can also see it here written. So you see that MUSE Wide, the widest of all the surveys, detects the brightest Lyman-alpha emitters. Then we go a bit deeper, MUSE Deep, and you see that the Lyman-alpha emitters that we detect are a bit fainter. And then you go to the deepest of all the surveys, you go to MXDF, and the Lyman-alpha emitters that we detect are the faintest of the 3 surveys. So in the beginning of my PhD, we started focusing on the MUSE Wide survey, just thinking about the statistics. The MUSE Wide survey is the widest, so we will detect the most amount of Lyman-alpha emitters, and we will cover the largest area on the sky. So this will give us better statistics when we measure clustering. So now I will focus only on the MUSE Wide survey. You see again the spatial distribution of about 1,000 Lyman-alpha emitters that we have in the MUSE Wide survey. And in the color bar, you see the redshifts of all the Lyman-alpha emitters. In the down panel, you have the redshift distribution of all those Lyman-alpha emitters. So in red, you see a computation I did for the expectation of the redshift distribution of a random sample. And in blue, you have the real redshift distribution of our objects. So as you can see, all these spikes that we have in the real data And all these values that we have with the real Lyman-alpha emitters are already giving us a hint that our Lyman-alpha emitters are going to be clustered. The distribution looks very different from what is expected from a random sample. However, this data is quite challenging for clustering studies. So two-point correlation function statistics exploit the spatial distribution of your survey. And in the case of MUSE, that is really small. However, we have a really large redshift coverage. We go from 3 to 6 in redshift, and in terms of cosmological volume, this is huge. So ideally, we would want to have a method that exploits that redshift distribution rather than the spatial distribution of MUSE. And this is why we are following a different method. We follow the K-estimator that was presented already in 2005, but the idea is pretty similar to the one of the two-point correlation function. The idea will be also about counting pairs of galaxies in your real data. But in this case, we will not need a random sample. So all the clustering information, we are going to obtain it from the real sample of galaxies. So if I show you the visual representation of the method and also the equation, the idea is the following. So what you see here is a sample of cylinders, each of them with a different radii, and also with a different depth determined by these 3 parameters. So the different radii of the cylinders are just bins that I make in transverse distance between the galaxy pairs. So these are just bins I make. And then you have the different depths of the cylinders, these 3 parameters, which is exactly the same, but for line of sight distances between galaxy pairs. And these will be 3 fixed parameters that I fix from the beginning in such a way that I optimize the signal to noise. So we can forget about these 3 parameters. I will just fix them, making some tests. So the idea of the K-estimator is now you will take this whole sample of cylinders, and I'm going to place the center of all these cylinders on top of my first galaxy in the sample. So if I do that with the K-estimator, I need to count the galaxy pairs that fall within this blue inner cylinder. And that number of galaxy pairs will be our numerator of the K-estimator. And then that amount of galaxy pairs, I'm going to compare it with the total amount of galaxy pairs that falls within the red plus blue's inner cylinder. And that will be our denominator. So in that way, I obtain the first data point for the K-estimator for our first transverse distance bin. Then I do the same with going into larger cylinders. So I go to the second transverse distance bin, and this means that first I will count the pairs of galaxies that fall within this second blue cylinder, our numerator, and compare that to the total number of galaxy pairs within the second cylinder. And that will be our denominator. And like this, I will go on and on, extending the radii of the K-estimator. And in that way, I will obtain these clustering measurements as a function of transverse distance between galaxy pairs. So just to mention, this K-estimator is theoretically related to the two-point correlation function. So in fact, if you have the K-estimator, you can derive the two-point correlation function and the other way around as well. So let me now apply this method to the MUSE-wide sample of Lyman-alpha emitters. So if we do that, I plot on the y-axis the K-estimator, so the clustering information, as a function of transverse distance between the galaxy pairs. This straight line here in black that I show you is the no clustering baseline. So if our data points would fall on this straight line, it would mean that there is no clustering in the sample. The objects that we are studying would be randomly distributed. However, what we see or what we measure is this clear clustering signal here, which is much above this 0 clustering line. And this is already telling us that Lyman-alpha emitters, at least in the MUSE-wide survey, are clustered. They are tracing some kind of a structure in the universe. Now, if we want to obtain some kind of mathematical information for the clustering strength, for example, only a signal doesn't tell us much, rather apart from this. So we need to kind of model, or we need to feed this clustering signal to obtain the clustering information in a mathematical way. So the easiest way of doing this, which is only an approximation, as I write here, which seems to be working at larger scales, is assuming that your clustering or your correlation function follows a power law. A power law that has 2 parameters, one slope, gamma, and one correlation length that we call. And these 2 parameters together will give you an idea of how strongly your galaxy is clustered. So if I make this first assumption, I can obtain just with a chi-square minimization, which is the best fit to our data. And this is what I'm plotting here in green. And this corresponds to these parameters I show here, most importantly, a correlation length of 3.6 eco-moving megaparsecs. So before MUSE arrived, this was everything that people had done before with clustering of Lyman-alpha emitter studies. They all had narrowband surveys, so they all had approximated redshifts, let's say. They didn't have spectroscopic redshifts like the ones that MUSE provides. And they all assume that clustering follows a power law. So this is, as I said, this is just an approximation. This is not the best way of doing it, but still I can compare my result to the previous studies in the literature. So clustering or correlation length, if you want, as a function of redshift. The big star is the result I just showed you. And the other data points are the previous studies of clustering of Lyman-alpha emitters. And you see that they all fall basically on the same line. So our results are also consistent. Now, using these two parameters, this correlation length and slope, we can derive something called a bias factor. So the bias factor is telling you really your clustering strength in your sample. And in fact, it tells you how your galaxies or how much more your galaxies clustered in comparison to the dark matter clustering. And from this bias factor, we can derive a dark matter halo mass, a typical dark matter halo mass for our sample. So I make all those calculations and I obtain that the typical dark matter halo mass for the Lyman-alpha emitters in the MUSE-wide survey, it's something like 10 to the 11 solar masses. As I said, this is based on assuming that the correlation function follows a power law, but this is not the state of the art. This is not how people do these kind of things right now. So the usual way that it's now thought to be the best way of modeling a clustering signal is by using halo occupation distribution models, or HOD models from now on. So let me just tell you a bit more about these models. So when we apply a power law to the clustering signal, the only thing we can obtain is a typical dark matter halo mass of our sample. Now, if you apply HOD modeling, you can obtain much more information than that. You can actually obtain the distribution of galaxies as a function of dark matter halo mass. So in other words, you will connect the way observers see the universe, so just a bunch of galaxies on the sky, with the way that theorists see the universe, so this structure of dark matter. And you will combine it in such a way that I will be able to give a recipe on how to populate dark matter halos with individual galaxies. And when I talk about galaxies, I will differentiate between central galaxies, so the galaxy that sits in the center of your dark matter halo, and satellite galaxies, the other galaxies that are around that central galaxy. Now, how HOD models model the clustering of a galaxy sample? So the way they do it is by distinguishing the contribution of galaxy pairs that come from the same dark matter halo. This is what is called one halo term. This comes from very small scales. And they will distinguish that contribution from the contribution of pairs of galaxies that belong to different dark matter halos. These at much larger scales, and this is what we call the two halo term. So the two contributions together from small and large scales will give me a total correlation function. That all this, of course, all this is parameterized. And these models are provided by Takamitsu. I just apply them to my data. So first of all, because HODs care about the small and the large scale in different ways, the first thing I have to do is I need to make the clustering measurements also covering the small scales. So just for you to see the difference, in red, I show you the previous clustering signal that we were measuring, only keeping it at large scales, because there we were just applying a power law fit. And I have done those measurements, those same measurements at small scales. So at the scales that are relevant for the one halo term, or these small HOD modeling clustering scales. So now we'll only focus on the total clustering signal, this one that covers the small and large scales, and I will find the best HOD fit to my data. So that is what I represented in black. And I also plotted two different contributions. So in blue, you see the contribution from the one halo term. So from pairs of galaxies that belong to the same dark matter halo. And I also separated it from the two halo term, clustering contribution that comes from pairs of galaxies that belong to different dark matter halos. Now, from this kind of plot, I can already derive a typical dark matter halo mass. And if I do that, it's basically the same as the one we obtained with a power law fit, but much more precise than before. However, I promised we can get much more information from applying HOD models. And in fact, what we can get is the number of Lyman-alpha emitters as a function, sorry, it's cut again, of dark matter halo mass. So this is the recipe I was talking about before. This is a recipe on how to populate dark matter halos with individual Lyman-alpha emitters. So in black, I show you the total number of Lyman-alpha emitters. This red shows you the number of central Lyman-alpha emitters. So either we have 0 central Lyman-alpha emitters or 1 Lyman-alpha emitter. And then you have the amount of satellite Lyman-alpha emitters in blue. So let's say we have a dark matter halo of 10 to the 11 solar masses. At 10 to the 11, we are at the number of galaxies of 1. So this means that in a 10 to the 11 solar mass halo, we can only have one central galaxy, one only Lyman-alpha emitter. If we have a slightly larger dark matter halo, something like 10 to the 11.7 or so, we are at the number of galaxies of 1.5. So this means that that dark matter halo can have one central Lyman-alpha emitter, and then you have 50% chance of having a satellite Lyman-alpha emitter. If our dark matter halos are even larger than that, let's say 10 to the 12 or so, we are at the number of galaxies of 2. And this means that we can have one central galaxy and one satellite galaxy being hosted by that dark matter halo. Now, from this kind of plot, I can also obtain, for example, more information on how many central Lyman-alpha emitters I have in my sample, or how many satellite Lyman-alpha emitters I can have in the sample. So if I make those calculations, I obtain that 3% of the Lyman-alpha emitters I have in the sample are actually satellites. So, or in other words, 2 out of 65 Lyman-alpha emitters in our sample are satellites. So the most common scenario for this sample of Lyman-alpha emitters is that in which your dark matter halos only host one central galaxy. And in really rare occasions, you will have some satellites in there. Now that was all for the MUSE-wide survey. Now we can go to the deeper surveys. We can go to MUSE-Deep and MXDF because, as I said, the different exposures will detect Lyman-alpha emitters with slightly different properties. So perhaps the different surveys will cluster in a different way. Perhaps not, but we want to check that. So on top, I show you again the results for the MUSE-wide survey. You have seen them before. And now the lower you go in row, the fainter you go in Lyman-alpha luminosity. So the second row corresponds to the results in MUSE-Deep, and the last row corresponds to the results in the deepest survey, in MXDF. On the left, you see the best fits to the clustering signal. And on the right, you see the HOD, so the number of galaxies as a function of dark matter halo mass. And on the right, you see something quite interesting. You see that the fainter we go in Lyman-alpha luminosity, the more to the left these HODs are being shifted. So this means that the fainter your population is, the smaller the dark matter halo masses needed to host a central galaxy or a satellite galaxy become. So it seems that there is some clustering dependence on Lyman-alpha luminosity. There is at least some change depending on the luminosity of your survey. So in order to investigate this a bit closer, we again take the 3 surveys, and I will split them to have subsamples at the median Lyman-alpha luminosity of the sample. So in that way, I will have 6 subsamples where I will do the same. I will measure the clustering, I will fit that clustering, and I will obtain the HODs and the typical dark matter halo masses for each of those subsamples. So just to show you the result, on the y-axis, I have the typical dark matter halo mass as a function of Lyman-alpha luminosity. The 3 colors are the 3 same surveys, as always. The filled symbols correspond to the full survey, and the empty symbols are the subsamples that I have just made. And what you see here is a clear clustering dependence on Lyman-alpha luminosity. In fact, we found that bright Lyman-alpha emitters, so the ones in the MUSE-wide survey, for example, cluster more strongly and reside in more massive dark matter halos. So something like 10 to the 11.5 solar masses for the halos. The faint Lyman-alpha emitters, so those in MUSE in MXDF, cluster much less strongly, and they reside in much smaller halos, something like 10 to the 10 solar masses or so. So this clustering dependence on Lyman-alpha luminosity has actually many implications that we discuss many of them in the papers, but I will only talk about one of the implications, which is actually the project I'm working on right now. So there is one implication that relates to the circumgalactic medium of the Lyman-alpha emitters, or also what is called as the extended Lyman-alpha gaseous halos around the Lyman-alpha emitters. So in order to visualize the circumgalactic medium of Lyman-alpha emitters, we need to go back to the MUSE cube, to those MUSE data cubes that the instrument directly detects. So if we go to those cubes and we go to each single Lyman-alpha emitter that is there detected, we can make a narrowband image of those Lyman-alpha emitters, a pseudo-narrowband image if you want. I show you some of those pseudo-narrowband images. In the center, you see the Lyman-alpha emitter, so that in red. And around that, what you see is diffuse Lyman-alpha emission. So this is the circumgalactic medium of the Lyman-alpha emitter, or also what is called the extended Lyman-alpha halo of the Lyman-alpha emitter. So in order to see this in a more mathematical way, what you can do is you can put annuli around the Lyman-alpha emitter, and you can measure the surface brightness within each of these single annuli. So if you measure the surface brightness within each of those annuli, you can have a Lyman-alpha surface brightness profile. This is just the radii of the single annuli that you see in this image here. And this is in blue, the Lyman-alpha surface brightness profile that is measured in individual Lyman-alpha emitters. And if we compare that to what is expected from a point source here in red, the PSF, you see that the Lyman-alpha surface brightness profile is very much extended from what is expected from a point source. However, at larger scales, these measurements become very noisy. So in order to counteract this, the usual thing that people do is they take all these images, they stack them all together. So basically you sum up over all the flux of these Lyman-alpha emitters, and you obtain a single profile for the whole sample. So this is the kind of profile, Lyman-alpha surface brightness profile, that you obtain when you stack all those images together. And again, you see the clear extension if we compare it with the point spread function there. Now, you do not only see these Lyman-alpha halos around Lyman-alpha emitters. Actually, when you point MUSE at any region of the sky, for example, I show you here the Hubble Ultra Deep Field. If you point MUSE there, you see that most of the sky is covered with Lyman-alpha emission. So not only Lyman-alpha emitters have these extended Lyman-alpha halos around, but most of the sky is covered in Lyman-alpha. And this is something my supervisor found some years ago. So now, in order to explain this kind of emission, there are many processes that contribute to these extended halos covering most of the sky. So the Lyman-alpha emission scatter, so those photons can scatter outside the galaxy. You can also have some kind of in situ recombination. So if the hydrogen atom recombines already in the CGM of the galaxy, that will power also the Lyman-alpha emission. You can have fluorescence process. You can also have some external sources contributed to this emission. You can also have cooling of gas falling onto the galaxy that also produce Lyman-alpha emission. But there is something that in the last years, there has been a huge discussion coming from simulators only. And those papers find that part of this emission is not only coming from these physical processes, they are coming from the emission from what they call faint satellites. And the things like all instruments are, or the instruments that we use to measure to detect Lyman-alpha emitters, they are flux limited. So below a given threshold, you will not detect any Lyman-alpha emitter, and above that threshold, you will detect them. So this is what they refer as faint satellites. They refer as undetected Lyman-alpha emitters under current instrumentation. So the emission from those undetected sources, when you do those stacking experiments to measure the surface brightness profiles, will contribute to this extended emission. But there is right now no observational paper trying to address this, and that is why that is the goal that we set for ourselves. So we basically want to know how much those faint satellites or undetected Lyman-alpha emitters actually contribute to those extended Lyman-alpha halos that we see on the sky. So in order to answer this question, I need two ingredients. First of all, I need to know which is the average surface brightness that comes from these unresolved sources. And then I also need to know how much the spatial distribution of those sources will boost or will enhance that average surface brightness that I will compute from the luminosity function. The second ingredient, I will constrain it with something that I call the boosting factor. But let me just first go to the first ingredient. So what you see here is the luminosity function, the Lyman-alpha luminosity function. This part here is what has been measured by the MUSE collaboration. And this straight line here is the MUSE detection threshold for Lyman-alpha emitters. So below this, you do not detect any Lyman-alpha emitter, and above that, you detect all the Lyman-alpha emitters. So the part that we care about is this undetected part of the luminosity function, which I have extrapolated to very faint luminosities that simulators are predicting that those galaxies may be as faint as 10 to the 38.5 or so in Lyman-alpha luminosity. So if I combine this part of the undetected luminosity function with the typical narrowband filters that are used to create those pseudo-narrowband images, I can obtain this average surface brightness that is expected to be contributed from unresolved Lyman-alpha emitters in a given narrowband width. Now, the second ingredient is something that I call the boosting factor. So the boosting factor tells you how much the spatial distribution of those unresolved sources is going to enhance or is going to boost this average surface brightness that I computed from the luminosity function only. So in order to calculate this boosting factor, I need to know what is the clustering of those unresolved sources. But since we do not detect those sources, I cannot directly measure the clustering of these undetected Lyman-alpha emitters. And therefore, I need to make some assumptions. And the first assumption I'm going to make, which is quite strong and we know is not really correct, but it's just a first step, I'm going to assume that the unresolved sources cluster like the ones that we detect. And we know it's not correct because of this clustering dependence that we found on Lyman-alpha luminosity. So undetected sources are definitely fainter than the ones that we detect. So we also expect that their clustering is lower than the ones we detect. Still, we make this assumption just as a first step, and I will first assume that the unresolved sources cluster like the ones in MUSE-wide. So you see the correlation function for the MUSE-wide Lyman-alpha emitters. So from this correlation function, I can obtain the boosting factor. And this tells me that if unresolved Lyman-alpha emitters cluster like the ones in MUSE-wide, that average surface brightness that I computed is going to be boosted or is going to be enhanced by a factor 10 to 20 or so. We can do it a bit better. We can take the faintest of all our surveys. We can take MXDF and do exactly the same. MXDF is already 1 order of magnitude fainter than MUSE-wide, but we know it's still detected. And if it's still detected, it's still brighter than those Lyman-alpha emitters. So these will be still be upper limits. In order to get the closest as we can to the real clustering of those undetected sources, I'm going to go back to this clustering strength versus Lyman-alpha luminosity relation. And what I'm going to do, I'm going to extrapolate the HODs that I found for the MXDF Lyman-alpha emitters and the HOD models that I found for the MUSE-wide Lyman-alpha emitter. Sure. Mm-hmm. If you take these three. Sure. Yes. So here they are asking, well, I've been calling this the clustering dependence on Lyman-alpha luminosity, and here they are wondering why, if we only take the full sample, so the field symbols only, it looks like it's a straight line. Well, to me, it doesn't look like it's a straight line first. So there is some kind of increasing towards higher masses. But that is why we made subsamples in order to investigate this further. So in order to have really, really faint and really, really bright and see, if you compare the faintest subsample with the brightest subsample, you see a huge difference. But right, when you do not make any subsample, it's just a tendency, let's say. Right. So then I extrapolate the HOD models down to very faint luminosities. And then I obtain a extrapolated HOD. Yeah, it's not super straight, but still, I will extrapolate the HOD models from the faint and the bright surveys. And I will obtain some kind of extrapolated, this is of course an estimation, is based on an extrapolation, but I will obtain the clustering of those unresolved sources. Again, extrapolation with many assumptions, but we believe this would be closer to the reality than assuming that those unresolved sources cluster like the ones that we detect. So now I will combine these three boosting factors with the average surface brightness that we have measured from the luminosity function to obtain the Lyman-alpha surface brightness profiles for clustered and also undetected Lyman-alpha emitters. And that is what we were looking for from the beginning. We were looking for that contribution of surface brightness coming only from satellites. You see here the three clustering assumptions. MUSE white is, of course, providing the highest surface brightness because it has the highest clustering. And this would be what I believe it would be the closest to reality based on those extrapolations. So now I can take these three profiles and I can compare them to what is measured in the literature. So if you remember, we would take all the images of the Lyman-alpha emitters, I would stack them together, and this is the profile that is obtained in the literature. Again, my supervisor there. So if I plot my satellite profiles on top of this total Lyman-alpha surface brightness profile, this is how it looks. So you see the three different colors are my three different satellite surface brightness profiles, and just an extreme case here in the dashed green line, where I have assumed that the unresolved sources do not cluster. There is no clustering. They are randomly distributed. And this is just an extreme case just to see how it compares. So we can obtain a lot of, this is preliminary, you don't see, but this is a preliminary result. This is not published yet. And you see, if we compare the total profile with my estimated satellite profiles, you see that my profiles are way lower than what is measured in the literature. So this means that the satellites, the effect from satellites is negligible at the small scales. If we go to a bit larger scales, let's say like 30 kiloparsecs from the center of the Lyman-alpha emitter, my satellite profiles are almost at the same height as what is measured, to what is measured in the literature. So this means that the contribution from satellites already at 30 kiloparsecs would start to become quite important in there. And if we go to much larger scales, something like 50 kiloparsecs, you see that all the satellite profiles are already above this total surface brightness profile. So this means that the satellites alone at these larger scales can already explain the whole extension of the Lyman-alpha halos that are seen on the sky. So let me just quickly conclude. What have we found? So we have found a strong clustering signal in the three MUSE surveys for the Lyman-alpha emitters. We have calculated typical dark matter halo masses between 10 to the 10 to 10 to the 11.5 solar masses, depending on the luminosity of the sample. We have found what I think it is a strong clustering dependence on Lyman-alpha luminosity, where the high luminosity Lyman-alpha emitters cluster much stronger than faint Lyman-alpha emitters and reside therefore in more massive dark matter halos. We also saw how the HODs were shifting to the left when we were going to fainter luminosities. Then we have, well, I've only told you about one of the possible implications of this clustering dependence, which relates to the extended Lyman-alpha halos around the galaxies. And we have investigated how strong is the satellite contribution to those halos. What we have found, and as I said, this is preliminary, we have found that the satellite contribution is negligible at small scales. It gains importance at the scales around 30 kiloparsecs, and it could be completely dominant at larger scales. Thank you.
Thank you very much. Do we have questions here in the auditorium? Carlos y después Jesús.
Thank you, John. Very nice talk. I have also done two-point correlation functions for a very different kind of objects in molecular clouds. And I was curious about the first time when you constructed your two-point correlation function from the wide field, and you showed this how the curve with the blue points.
Mhm.
Right. I wonder if those structures that you see there, you see like a straight slope and then a bump
Mhm.
and then another straight slope. If those could be related to what we found in maps of molecular clouds. In maps of molecular clouds, we are limited by two parameters. One is the resolution. We cannot really resolve smaller structures than what our what we can really resolve with our beam or whatever we use. And the other one is the size of the map. At some point, you are opening your cylinders in your case, but your cylinder will be compatible or wider than the size of the map, and at some point you're gonna have a limit, right? That's why the function trumps at some point. But on the other side, you're limited by how faint a galaxy you can detect. Can you just say some more about that, and also about if you have an idea of why that thing bump
Mhm.
around, I don't know, like what is like 7 or so?
Yes. Okay, thanks for the question. Right, you're right. So we cannot keep extending the cylinders of the K-estimator up to infinity. We are limited by the size of the sample. So by measuring the size of the sample, we can go out to 20 comoving megaparsecs or so. So I was already careful enough to just cut it at half so that we are not limited by this edge of the survey. And then, of course, at the small scales, we are limited by this resolution of the instrument. We do not, or we cannot detect two close pairs just because of the resolution of the instrument. So in principle, I cannot go smaller than a given distance. This bump here, so in the first paper, we were really puzzled by this. And we actually did a lot of tests because in the beginning, we thought maybe there is some kind of substructure in the sample or something like that. And we did a lot of tests, and the conclusion was that this is a statistical fluctuation because each of these data points is kind of correlated. So in fact, if you put one of these points slightly higher, the points that are around are going to follow. So it might happen that one of these points went up and the others just followed it. And in fact, I checked that when I change the beams, this bump disappears. So it's just a statistical fluctuation. Mm-hmm. Welcome.
Ok, tenemos en Zoom Silvia Torres.
Well, thank you for your talk. It was wonderful, but I mean, it's difficult for me to follow because it's not my field. I find that, can you please explain the last graph once more? What are exactly those points? And I follow your proposal of the different estimators or whatever you want to call them, but I could not understand the final graph. So can you please repeat or explain it in another way?
You mean this graph, or you mean the last graph?
No, the last one, the very last one in your talk.
Uh-huh. This one.
Yes.
Uh-huh.
So again, what are those points, the black points? What exactly are they?
Yeah.
And why do you say that you can go from one distance to another with some confidence?
Yes. So these data points that I showed there are just the measurements. Yeah, the measurements of surface brightness that you can measure within this annuli. So basically, I measure the flux that falls within each of these annuli, and that gives me some kind of surface brightness profile as a function of the radii of this annuli.
And you have them stacked together, all of them stacked together?
So I can do that for each of these individual Lyman-alpha meters, and that
Okay.
I stack all together. And that gives me one single profile for the whole sample of Lyman-alpha meters.
Okay.
Yeah.
So those are those black points. And then how do you compare one thing with the other? That's the most difficult part for me.
How do I compare those data points to?
With your assumptions, with your green lines and red and blue lines.
Yeah.
On the last graph.
So that stack profile just comes, so includes any kind of emission that you have within this annually. So any kind of physical process, any kind of satellite that we do not detect, it will be included in this stacked profile.
Okay.
Now, the estimations I make are only for satellites, and I only considered, well, I had to make some assumptions on how faint those satellites may be. I also need to make assumptions on the clustering of those sources. But the profiles I show only come from satellites or from undetected Lyman-alpha meters. So while those data points come with any kind of contribution, any kind of physical contribution, these profiles that you see in there as colors only come from the emission from undetected sources that are clustered, because I have assumed some clustering, and they are as faint as 10 to the 38.5 that I have assumed. So that's another assumption.
Okay. So you say that, and your conclusion there, which was?
So my conclusion here is that the undetected sources do not contribute to this stack profile almost at very small scales, but at scales around 30, maybe I point in the PowerPoint so you see. So at the scales of 30 or so.
They are comparable.
Yeah, exactly, they are comparable. So from here, the satellite contribution, it's gaining a lot of importance. And above 50 kiloparsecs or so, the satellites are already higher than the profile that is measured. And this means that the satellites only, the emission from those satellites, can already explain the whole profile that is measured from the literature.
Okay, well, thank you. Thank you. Sorry.
You're welcome.
Okay. More questions here? Okay, Michael.
I have another question about this graph. Should we, if we really believe the last point, we should really conclude that there are no satellites contributing to this profile, because all of the contributions are above what's observed.
Yeah, but that is giving me a different kind of information. That is telling me that some of the assumptions I have made maybe are not that right. So because this contribution is already higher than what is measured in the literature, it might be that the extrapolation I made in the luminosity function is not really what we should do. We have a lot of uncertainties here. So the slope of the luminosity function is really uncertain, and having a steep or a shallow slope will give me a very different kind of contribution. So it might be that the extrapolation shouldn't be done in that way. It might be that the satellites are brighter, and that will decrease this contribution. So this is telling me that some of the assumptions we are taking right now are perhaps not ideal. Yeah.
Okay, and I had another, if I may, another question about the halo occupation distribution, how that varied with luminosity. And what I wonder is, for the deepest sample with the lowest luminosities, you always assume that if you see one, it's a central galaxy.
Yes.
But what if it's a satellite?
So that is one of the assumptions of HOD modeling. The first galaxy in a dark matter halo is always the one that we put in the center. So the first galaxy in a halo, it's always placed in the center in the model. So therefore it's a central. Yeah, so we cannot have one satellite without having one central. But that is just the assumption of the HOD modeling.
Okay, ¿más preguntas aquí en el auditorio? ¿En Zoom? No. Okay. Si no, vamos a agradecer otra vez. Muchas gracias por tu plática.
Gracias. Muchas gracias.
Bueno, y las esperamos y los esperamos la siguiente semana para el coloquio. Que tengan buen día.